Good morning. Today let us study about potassium iodide water two component system. It is also an eutectic system. It is an example of eutectic system. It is a binary system. It is also called a binary system because there are two components. It is called a binary system. If you look at this, potassium iodide is a salt. This is a salt water system. In general, the melting point of salt is very much the salt has the highest melting point. You have studied in ionic compounds. The differences between ionic compounds and covalent compounds. Therefore, the melting point of salt is very much higher than the melting point of water or the critical temperature of water. What is critical temperature of water? Please, you see the one component system, water. At critical temperature of water exists only in gas phase, that is in vapor state. So, it is for example, lead water system, lead silver system is also two component system, eutectic system. Melting point of lead is represented here and melting point of silver is represented here, but it is not possible to represent the melting point of ice, melting point of water, ice, and melting point of Ka because it is very much greater than the critical temperature of water, I said. So it is not possible to represent the melting points of both the components, A and B, A and water and Ka. Okay. Now let us see. Reduced phase rule is why reduced phase rule is applied to describe the phase diagram of this Ka water system, salt water system. Why reduced phase rule is used? Let's see now what is the reason. Here for two component system C equal to 2, for minimum phase you have studied minimum phase P equal to 1. Then you use the normal phase rule, F equal to C minus P plus 2. Therefore, on substituting C equal to 2, P equal to 1, you will get 3. Therefore, there are 3 degrees of freedom required to define the Ka water system. There are 3 degrees of freedom required to. So, the 3 degrees of freedom, for example, temperature, pressure, composition. Composition means 100% water, you add Ka. To the ice, you add Ka. Therefore, temperature, pressure, concentration or composition. So, there are 3 degrees of freedom cannot be represented in 2D plot. We need to describe in 3D plot. So, instead of that, we keep the pressure constant. For this system, the pressure is kept constant, that is 1 atmosphere. Therefore, the 2 represents temperature and pressure. Therefore, the reduced phase rule is therefore used to describe this system. F equal to C minus P plus 1. Okay, this is called a reduced phase rule. Okay, now a plot of, so in this there are 3 degrees of freedom, pressure is kept constant. Therefore, there are 2 degrees of freedom. There are 2 variables to describe the system. Temperature, the plot of temperature versus composition or concentration of potassium iodide water system is called phase diagram. This is a phase diagram. You first draw the phase diagram. It is similar to lead silver system, but solubility curve. Here, melting point curve or freezing point depression curve. Here, one is freezing point curve and another is solubility curve of Ka, not the melting point curve of B. Okay, remember that. And label the phase diagram. Solution phase, solution plus ice, solution plus solid, solution and eutectic mixture plus ice and eutectic mixture plus solid Ka. Okay. So now let us look at the characteristics of the phase diagram. What are the important characteristics of the phase diagram of Ka water system? There are 3 important characteristics. One, AC curve, another is BC curve and eutectic temperature. Okay. So the AC curve is called a freezing point curve or freezing point depression curve. For example, let us take a beaker with the crushed ice, with the powdered ice, crushed ice, okay, and a glass rod and thermometer. using thermometer, the temperature is noted. What is the freezing point of ice? You know, what is the melting point of ice or freezing point of ice? Both are same. Okay, the freezing point of ice equal to 0 degrees Celsius. This is 0 degrees Celsius when you take ice 100%. When you take ice 100%. Okay. Now on adding, now you add K to the ice. What will happen? The freezing point. For example, you have taken 100 gram of ice. You add 1 gram of Ka. Now, on adding Ka, addition of Ka decreases the melting point. The melting point decreases or the freezing point decreases on further addition. Okay. And also concentration of Ka increases. Concentration of Ka increases and the melting point, freezing point decreases. And the concentration of Ka increases. Okay, along the phase now, you see, along the phase, there are two phases. Solution phase and ice, solid. Solution and ice. Therefore, let us apply the reduced phase rule to calculate the degree of freedom. This is commonly asked in JAM and other entrance examination. P equal to 2. There are two phases similar to one component system and two component system. You have earlier studied. Please watch those videos. F equal to C minus P plus 1. By applying reduced phase rule, the degree of freedom is equal to 1 because the pressure is kept constant. Pressure here, this is pressure, not phase. Pressure is constant. Okay. Therefore, along the curve, the system is univariate because F equal to 1, it is univariate system. On further addition of Ka, the point C is reached. The point C is called eutectic point. The point C is called eutectic point. The two curves AC and BC meets at a point called eutectic point. At this point, there are three phases coexist: solution, ice, and solid Ka. There are three phases at this point. Therefore, applying the reduced phase rule, P equal to 2 and P equal to 3 here, because there are three phases, C equal to 2, F equal to 0, and this point, the eutectic point, is invariant point. And what is the eutectic temperature? This is the lowest temperature that is attained, that is reached by the addition of Ka to the ice. This is the lowest temperature that is attained or reached. Okay, so what is the eutectic temperature? This is 0 degree, so on minus 23 degree Celsius. This is the eutectic temperature. And what is the composition at this point? If you look at the eutectic composition, is the composition at point C. At point C is 52% Ka, that is 48% water. Okay. This is called eutectic mixture. If you look at under microscope, there are eutectic mixture consists of crystals of water and crystals of ice, and crystals of Ka. Therefore, it does not. The two components do not form a compound. It forms a mixture. That is called eutectic mixture. Okay. Now, on further. At point C, on heating, no change, initially no change in temperature. See, when you heat, there will be increase in temperature. But at point C, there is no change in temperature as long as three phases coexist. Remember, okay? On further heating, you are heating and the addition of K. On further heating, you are adding K. On further heating and addition of Ka, ice is, you see, along the curve, ice is converted into heat. Since you are heating, ice is converted into water. Okay, on further heating, addition of Ka, ice is converted into water and solid Ka appears. Because you are adding Ka in excess. See, you are 52% more. You will be adding excess Ka, therefore solid Ka appears along the curve. Therefore, solution is in equilibrium with the solid Ka. Therefore, by applying the reduced phase rule, F equal to 1 along the curve, the system is univariant. Okay. Now let us take a point at A. Let us take a point at A. At point A, it is in solution. It consists of water and Ka dissolved in it. No compound is formed. Remember, no compound is formed. On cooling, at this point, what is the degree of freedom? It is commonly asked in entrance examination. At this point, it is bivariant. Remember, at this point, it is bivariant. On cooling, see, on cooling, it reaches point B. On cooling, it reaches point B. There is no change in composition. A and B have the same composition. Remember, on cooling, it reaches, on cooling, temperature decreases. On cooling, it reaches point B. And no change in composition. A and B, they will ask in competitive examinations, A and B have same composition, but A is bivariant and B is univariant because it is along the curve. It is in the curve, therefore it is univariant. Point A is bivariant because only one phase is there. Here there are two phases there. By applying reduced to phase rule, we can calculate the degree of freedom for point A and point B. And along with then, after reaching the point B, on further cooling, it will follow BC curve. See, then it follows on further cooling, it will follow the BC curve and reaches eutectic point C. On further cooling, ice will separate, and the eutectic point is reached, and the solid Ka also appears. Okay, so they will ask what is the degree of freedom at point A, what is the degree of freedom at point B, and what is the degree of freedom at point C. At point C, F equal to, there is no degree of freedom required to describe the system, F equal to 0. Okay, so they will ask such questions. Okay, so you draw the phase diagram and label it and understand before you answer any questions. Thank you for watching.